Okay. So we're going to take a look at what's called a point mass and an extended object. So remember the 50-pound weight you lift up versus lifting a couch that's 50 pounds. They're very different to lift, right? That's the first thing we're going to look at. Then we're going to look at what's called the net torque, or the total torque. And that's what you guys just did, actually, by looking at the mass times the length in the center. That's the actual torque itself. And then we'll talk about what's called rotational equilibrium. So let's take a look at the first slide here. And this is exactly what we were just talking about. See this dot on the left of this actual member here? This dot is the rotational axis, or the fulcrum. So this right here is where it's going to rotate about. Where's the force applied? The force is applied at some distance from the rotational axis. The distance between these two dots right here. That's how far away it is. When you guys just did that experiment, you had maybe one option here, one option here, and one option here. And those changed. You could have hung the mass here and the R value had been 1. When you hung the mass here, remember the R value was 2. When you hung the mass out here, the R value was 3. So what you noticed in your lab was this relationship right here. Tau, which is torque, let me explain this one. This is called tau, equals R times F. That's what you came up with in the lab. The sine theta part we'll talk about in a minute. In your case, you don't have to worry about it because theta was 90 degrees. Think about this. When the mass hangs, which way does the weight of an object pull always? Down. So what's the angle between the horizontal and down? 90. Okay, so we didn't have to worry about that in this case. The sine of 90 happens to be 1. So we didn't have to worry about sine of theta. I'll explain that in a minute. But I want you guys to all see that you literally just did this. R is the distance from the actual fulcrum, or the rotational axis. F was equivalent in the sense of the lab to the mass. As the mass got larger, what happened to the force of gravity? It got larger. But we call this F in general because it could be an applied force. When I just opened the door, I pushed on the door with the force F. I gave it a push, right? FP we've been calling that over here. In the lab just a minute ago, you guys really used FG, the weight of the actual mass that was hanging. But the concept here was that you multiply the distance from the fulcrum times the actual F value. And again, where is that seen? Right here. Distance from the fulcrum times the actual weight or mass hanging. Distance from the fulcrum times the actual weight or mass hanging. Those were equal to each other because the products were equal to each other. Now, you guys saw me open the door, so you can see this. Obviously, that torque causes something to rotate. The whole idea about torque is that it's rotational. So this next section, we're going to do, this is section 8.3, and then we're doing part of chapter 9, 3 of those sections. It's all about things that are rotating. If you want to explore more about this, honestly, if you take AP Physics next year, you do a lot with rotation. This is the most we're going to get into it, though, in this class, in chapter 8 and 9. But there's a lot more to do with rotational inertia and rotational mechanics. Think about anything that you ever move with. Anything that has moving parts usually rotates. Whether it's a ball bearing spinning, whether it's a wheel rotating, whether it's a conveyor belt moving, and there's rotations everywhere. I mean, look. Think about like even old school hard drives for computers. They used to actually sit there and spin. It was measured with RPMs, revolutions per minute. Now they're solid states, so they don't actually spin. They're very different. But that concept of things that are moving parts that are spinning constantly or rotating occur all over the place. I mean, I'm trying to think of it, and it's so much like this pencil sharpener right here. It's got a blade in the middle that's rotating, right? So a lot of things occur in life that are rotating. We're going to look at the basic laws of rotational mechanics in this chapter and the next. So sine theta comes into play because the idea is that generally the force applied should be perpendicular. It should be perpendicular to the axis. And you guys saw a minute ago when you did this lab, you guys hung a weight and the weight acted straight down like that. That's how it acted a minute ago when you drew it. So in your experiment there, this angle here was a right angle, so the angle theta was 90. Now if it's not 90, the angle theta is between the actual force applied and the R. The R is the actual lever arm. So the angle theta is between the force applied and the actual distance or direction along R. So here's theta in this case. That's theta right there. Okay, so you start at the fulcrum, you go along the lever arm until you hit the force, and then you go along the force, and the angle that's created is called theta. But the idea in this course is that in general, is that we notice that torque only affects things at a right angle. So let me explain this one more time a little better. Let me just hold this. Okay, just hold it. So it just serves like as if there was a rod over here. So the minute I do this, it rotates, right? The minute I push here, it rotates, push here. Now, what if I push this way? Hold this thing. What if I push this way? Is it going to move? Is it going to rotate, I should say, if I push this way? No. Hold it fixed. I don't want to move it, okay? Why is it moving? No, I mean hold it from moving left to right.
Oh.
Yeah, my bad. Sorry. Yeah. So why wouldn't it move? Why wouldn't it rotate when I push this way? But when I push this way, it easily rotates, right? But when I push this way, if I apply force this way, nothing happens. What's going on there? Explain what's happening. Sorry, that was a little confusing.
Well, it's because I think it's the angle you're kind of like pushing it at. Because if it's, if you have like a axis, I guess, and you push at the axis, at the actual point, it's not going to do anything. But if you push like a different direction, then it will.
Yeah, I mean, it's part of it's common sense, right? What Ryan's explaining is like a torque wrench, right? So if we look at a simple wrench, when we think about how a wrench works, a wrench uses torques to help you turn something. But of course, in this toolkit is the one with that. Whatever, this is fine. I can even use a set of pliers. If you were to use a set of pliers to loosen or tighten a bolt, right? So here's the actual, let's say I want to adjust these SOs. I put this here. If I push, it's not going to do anything. If I pull, it's not going to do anything. It's when I turn that this is able to rotate, right? Because the force I'm applying, look at my arm and look at the lever of the actual thing. What angle do you see here? 90 degrees. But if I do this and push straight up, is it moving? Is it rotated? What's the angle now? Yeah, either 180 or 0. Either one. Either way to say it. But when I'm like this, and I pull back, I see it rotates right away. I push that way, it rotates. So if I apply a force to something that is collinear, or along the same direction as the R value, it's not going to cause it to rotate. So take theta and move it all the way out, and think about it that way. That angle would be, as Will mentioned, 180. And the sine of 180 happens to be 0. So you don't create any torque when you apply a force that's parallel to the actual lever arm. R is the lever arm here, we call it. This is the lever arm. If you apply a force that is parallel to that, you do nothing to it. It's not going to rotate at all. The theta is 180 degrees, and sine of 180 is 0.
What if instead of putting his hands in the middle, he put them on the two ends? Would that change?
That prevents rotation because now you're fixing an object in more degrees of freedom. So
you still wouldn't be able to push it?
So if somebody held it like this, it can no longer be rotated or pushed. Think about it. Because what causes rotation? The unit axis to spin about. And if these are both fixed on these ends, can it spin? Yeah. So even if you push down on this end, it will move now. So the idea is that when you only fix something at one point, it allows rotation. But the minute you fix it, like if I just drilled into the wall, it can spin, right? But if I drilled in another screw right here, can it spin anymore? No. It's like a picture frame on the wall. When one of the hooks comes off, and now what happens to the picture frame? It swings, right? And then it sits there at an angle like this for the next 2 weeks until you or somebody in your family comes over and fixes it. The two nails provide rotational equilibrium. So it's the same concept. So the idea again is that we're always looking for the perpendicular force. So really, when we look at F sine theta, we're looking at this right here. Okay, because remember this is made up of two components, the X and the Y components. So take a look at that force. Look at the way I redrew it with the blue lines there. So those vectors there in blue, the vectors in blue are showing you that, yeah, if I apply a force down at an angle, it's like I'm pushing straight down and I'm pushing in. Think back to vectors. When you want to go, what is this? Southwest. When you want to go southwest, you go west and then south, or south and then west. So this force that's applied at an angle, it's pushed down and to the left. So the two blue vectors I just drew were down and to the left. But the vector drawn to the left has no effect on rotation because it's parallel to R. Remember that this vector right here, this vector has no effect because it's parallel to the R value. The R value in the diagram is the lever arm. So this is parallel to this. So this has no effect on it. So this is the only thing that has any effect. Well, it turns out, if you recall, that this is F cos theta, and this is f sine theta. Think back to your vectors. When you want the y component, you use sine. When you want the x component, you use cosine. So as a result, only the f sine has any effect on this problem. The f cosine becomes nothing. It's never going to have any effect. It's only the sine component. So as a result, if you look at your formula, I was trying to show you guys where the sine part comes into play. Instead of just taking r times f like we had in the lab just now, we have to multiply that f times sine theta. Okay, so that we know that we're only looking at the perpendicular component. So if my lever arm looked like this, and a force were applied like that, here's my theta now. Okay, it could be at any angle, doesn't matter. So if this was a lever arm, and we're applying a force, the r value would be from the point of rotation, which is the dot, all the way to where the force is applied. There's the r value itself right there. So this is the lever arm length. The applied force is represented by the black vector arrow right here. Theta would be between those two again. Okay, so we're always going to be looking at that. And when we use f sine theta, we end up getting the y component, which is this right here. This is f sine theta, in case you're wondering. That's what f sine theta looks like. That's f itself. F sine theta is always the vector that's what? It's perpendicular to the lever arm. That's why we use sine theta in the formula. Just like we used it over there earlier. Okay, so what I want you to gain from this is that sine theta is always used. Theta is the angle between the lever arm and the force applied. And whenever an object, or whenever something applies a force that is parallel to the lever arm, right? Like f cosine theta, if you push in from the right, we showed this a minute ago with Ernest. If you push in on the end of something, it's not going to cause it to rotate in this direction at all. If you're pushing in from the right in like that. So this is a diagram demonstrating exactly what I was talking about with the lever arm. Take a look at this torque wrench here. So the lever arm is the r value. It's like that distance from the fulcrum itself. So what you're noticing in this case is that you always, in this case first, I'll show you, you always have a length r from the fulcrum where it rotates. Here's the actual bolt that you're rotating, and here's the force applied. You always have a value r here. So we could think of that and we can consider, well, if I apply a force at an angle now, this r value looks like it's still the same length. And it is still the same length, really. And this r value is still the same length. It's still the same length. But what's happening is my theta is changing each time. My theta is getting smaller, 90, maybe 75, 45, and now the theta value here is like 10 degrees, maybe 20 degrees in here. So what's happening is the theta value is getting smaller and smaller. So you could think of your lever arm as r sine theta or r. It really doesn't matter either way you look at it. But if you think of your lever arm as r, then you have f sine theta as your force. But if you think of your lever arm as r sine theta, you have f as your force. So you can think of like lever arm times force, or lever arm times perpendicular force. Either way works, but notice it's the same thing, right? Both of these scenarios, either way I write it, if I write it as r sine theta f or rf sine theta, I get the exact same thing. So it becomes a little bit confusing, but you're noticing here, follow what I'm saying here. From here to here, and then look at this dashed red line, then look at this dashed red line, then look at this dashed red line. What's happening to the dashed red line from scenario 1 to 2 to 3 to 4? What's happening each time? Yeah, it's getting smaller and smaller. The lever arm, that distance is getting smaller than this one was because theta got smaller. Okay, it's tough to follow this diagram. This was in one of your, I think it was in actually this year's text, but it goes like this. Sorry, okay. So scenario 1 has the biggest lever arm because theta is 90. Then the lever arm gets smaller in scenario 2, smaller in 3, and it's the smallest lever arm in 4. And really what's happening here? It's like, all right, well, if I apply this force here, I have to consider the fact that this distance is getting smaller. If you don't want to like go crazy with the lever arm approach, just remember this is your formula you're going to use. R sine theta f or R f sine theta. Okay, either one works. But the idea is that as theta gets smaller, the the value of the torque also gets smaller. Okay, as theta gets smaller, the value of torque also gets smaller. The symbol is pronounced tau. It's a Greek symbol for the capital for the letter T. It looks like a T also. Okay, torque. As the theta value gets smaller, the torque gets smaller. Right. No? Stretch it. Honest?
So they're directly related.
Yeah, they're directly related, those two. From 0 to 90, I should say, they're directly related. After 90 degrees, it gets smaller again. So Ernest, from 0 to 90, as theta gets bigger, tau gets bigger, but then after 90, it gets smaller, actually. It's kind of weird, yeah. The way you would write that would be like a piecewise function. Ernest, here's how I would write. If you wanted to write it that way, you were writing with direct and indirect variation, I would write it like this. And then I would write this. Okay, that's how I would write what Ernest was just saying. So yeah, as theta gets bigger, tau gets bigger up until 90 degrees. But after 90 degrees, if theta keeps getting larger until 180, the tau value is going to get smaller and smaller. It's because your sine function, which you're going to learn more about this actually fourth quarter, I think, in math class. You're going to learn about the sine and cosine waves. The sine function, it's a function that is cyclic. It goes up and down like this. It literally looks like a wave. And from 0 to 90, the sine function grows. And then from 90 to 180, the sine function decreases. And you can actually just type in numbers and you'll see it will work. If you type in like sine of 10, sine of 20, sine of 30, sine of 40, it keeps getting bigger and bigger and bigger. And then after 90, the sine function gets smaller and smaller and smaller.
When is cosine involved? Like the lever has to be correspond to.
We're not even have to worry about cosine with torque. Yeah, don't even worry about it. It's a good question. Yeah, we don't have to use it here. Trying to think of an exception to that. No, we don't have to worry about it right now. So let's take a look at this scenario. Very simple question to start us off. You don't even have to really write much. You can just look and explain. Which of the following hands produces more torque on the bolt shown? So there's no angle given, so you could assume the angle is 90, right? Like how else would you pull on a wrench? You would pull on a wrench with a 90-degree angle. It wouldn't make sense not to. Yeah, they're equal. Does everybody see that they're equal? Take a look. One force is double the other, but the length of the lever arm is half. So the first scenario, so scenario A, you've got R, which is 1 meter, times the force applied, which is 20 newtons, times the sine of 90. And then scenario B is the same thing because it's 2 meters instead, but the force is only 10 newtons, and it's still sine of 90. Okay, so either case, your answer is 20. My units of torque, although if you remember force has the same units, it's not written as joules. It's not written as joules. It's written as Newton times meter. Okay, it's really annoying. They don't use the unit joules, even though it's the same unit, really. Right? Think about work. What was the formula for work? FD cos theta, right? F is measured in, D is measured in. So newtons times meters, right? With FD cosine theta for work, newtons times meters. Yet here it's not called a joule. Is that clear? It's not. I know it sounds weird because joules are newtons times meters. Here you don't replace this unit with joules. It's a little bit different because it has to do with rotational bodies here. The other one was not about rotation. All right. How about this one now? I'm going to give you, I don't know, 2 minutes. Try to hypothesize with your group member what you would do to start this, with the person next to you maybe. Think about what you would do to start a problem like this. This is pretty much your lab right here, right? Once you have an idea of what you're doing, start writing down the numbers. Figure it out. Once you have an idea, try to figure it out. And you need nomenclature for rotation that's positive or clockwise versus counterclockwise. Do you use anti or counterclockwise? When you were a kid, did you ever hear the term clockwise? So did you say counterclockwise or did you say anti-clockwise? Anti? How do you, what, yeah, because it's in French and you translate it?
Like anti-clockwise.
It translates to anti, right? It's so interesting. Because a lot of texts use anti-clockwise, like old text and stuff, or counterclockwise. It just means the opposite.
Yeah.
If you need help, use your formula. Use the formula you just wrote up a little while ago from your lab, or use the one on the previous slide or two. Keep in mind the angle on the far right is a little bit different, right?
I think I got it.
You got a number actually? Or good so far. Think about negative to positive. One of them would cause it to rotate one way.
Just because he said negative. So
You guys are good at
You really?
One of those should be negative. It doesn't matter, but in this class, so just so you guys know, in the course, we're going to assume positive is counterclockwise, which is annoying. It doesn't matter, you can do it either way.
No,
But I don't, it's something I gotta research why they're negative. But they consider counterclockwise to be a positive torque, and clockwise to be negative. The one pushing down the left will create a positive. I know. So, ready? If something causes the object to rotate this way, we consider it to be positive torque. Something that it doesn't matter. You can consider either direction, either way, as long as you're consistent in your problem. Okay? But we consider this to be negative torque if it causes it to rotate clockwise. If it causes it to rotate counterclockwise, we consider it to be positive torque. What would this first one do? Yeah, because look, ready? Here's how you picture, in case you're wondering. Please look up, please look up. In case you're wondering, visualize. Look, here's the scenario, right? Take a look, here's the scenario. If I apply only this force, which way will it turn? Counterclockwise. If I apply only this force, which way will it turn? So this one creates a negative torque. This one creates a positive torque. Try to figure out which one creates more torque. Which of those two is greater? Good. Good.
You didn't notice that?
It's not just just put T though. That's to be and then the total net is 57.5.
So I heard the number. What's the number, Ernest?
For the total.
The answer, yeah.
Oh, 57.5 newtons.
Very good. Let's take a look. So the first force is going to produce a torque we'll call tau 1. And that force is at a distance of 4 meters, right? 4 meters from the actual fulcrum. We know that the force applied is 20 newtons. Since this alone would cause it to rotate counterclockwise, we consider this to be a positive torque. The second, well, I don't have to put an angle because it's 90, but I'll put it anyway. Okay, so that will give me a positive 80. The second torque is at a distance of 3 meters from the fulcrum. Notice that the 3 or the 4, sorry, this is going to become negative. The 3 or the 4 itself is never really negative. It's just the torque that I apply as a sign. So this sign is going to be a negative here, simply because this force would cause it to rotate in this direction, which is clockwise, and we're saying clockwise is negative. Okay, that could be your quick thing to write down. Counterclockwise is positive, clockwise is negative. So this negative sign has nothing to do with the R value. Is that clear? Yes? R itself, R is the distance from the fulcrum to where the force is applied. It's a distance, it's a positive value. R is not negative at all ever. Is that clear? R is the distance from the fulcrum to the point where the force is applied. R is always positive.
So that means you can make the force negative.
Yeah, but I just tack on the sign actually instead. Because for torque, it's all about which way a body rotates, not about if the force is up or down. You follow what I'm saying? Because I could put a force up on this side, which would be the same thing as putting a force down on this side. Follow me, please. Matei asked a great question. He said you could just make the force negative or positive. I said I wouldn't do that. I would consider the rotation. If I put a force up on this side, push up, it's the same thing as pushing down on this side, isn't it? So the direction of the force isn't really what matters. It's which way it would cause it to rotate that matters. So let's not apply negative or positive signs to forces. Let's simply apply them to the actual context of the situation. Now,
Technically, just like add it on to the answer.
correct. Yeah, that's great. So notice what Matei is saying. You're technically just like tacking it on. Yes. I just applied the positive or negative based on the rotation. Hey, why did I use 30 degrees? I told you guys to use the angle between the lever arm and the force applied, so we could have used this angle also right here. What's that angle? Careful. The supplementary. Right, supplementary? So, do me a favor real quick. Go to your calculator, type in sine 30. Type in sine 30, and then go ahead and type in sine 150. There you go. Yeah, it's the same answer, isn't it? So the sine of angles that are supplementary are the same. So the sine of 40 is the same thing as 140. The sine of 10 is the same thing as the sine of 170. So if I use 150 or 30, it doesn't matter. Okay? Doesn't matter. But to show you, this lever arm extends indefinitely like that. So see that dashed red line? I could measure my angle this way, which is 150, or this way, which is 30. So it doesn't matter how I draw this scenario. All I know is this is the angle either way between the lever arm and the force applied. So traditionally this is the angle used, but I gave you this angle. It's the same thing. This torque turned out to be, what was this again, guys? Negative 22.5. And both of these are Newton meters as units. So when we want to find out the overall torque, it says which way, will it end up moving? And if so, in which direction? So we sum the torques together. Look at my symbols, please. Okay, yielding an answer of 57.5 Newton meters. So since our answer was positive, we started the problem by saying positive is which direction? Which way is positive? Counterclockwise. So the answer is yes, it will move. Yes, it will move. In which direction? Counterclockwise. Okay, where does that answer come from? Yes, counterclockwise. It comes from the result of the net torque being positive. When the net torque is positive, we know that it's going to move counterclockwise. How are we doing? Okay so far? All right. Let's try to finish off today with one more. We have two more examples to do still, but let's finish off today with this one if we can. Is this any harder than the last one? Start with, please. What's the only difference then?
You have an extra
Applied force. Yeah, you have three applied forces here, right? You have three applied forces. You need to consider which way they rotate. You don't know the R value. You're trying to find the R value. It says the following. Determine the location where the 10 Newton force should be so that there's rotational equilibrium. So that it's what? What does equilibrium mean?
balance.
Balance. So pretty much what you just did with the lab, you have to figure out what hook should I put this 10 Newton force on? Right? You're determining R. So you have to think about what do these things create, positive or negative torque. So let's do this one together. How about right here? If I only apply this force, which way will it rotate? Only this force alone, which way will it rotate? Counterclockwise, because it would start to spin like this. Take the arrow, right? Here's how you do it if you don't know. Take the arrow and try to continue the arrow in a circle around the fulcrum. Here's the fulcrum right here. If I continue this arrow, follow my pen, it's got to make a circle by going like this, right? How about this one? Only clockwise, because if I push down on this side, it causes it to rotate like that. How about this one? Clockwise. I push up on this side, this is going to go up, right? If I push up, literally, this lever will go up here and it'll start to rotate like this. So if you're confused, you need to visualize this, guys. Okay? Ready? Push up, clockwise. Push down, clockwise. Push this one down over here, though, counterclockwise. So the 25 Newton force is the only one that produces counterclockwise rotations. Okay, it's the only one in this scenario that does that. The other two, the 15 and the 10, both provide clockwise rotations. We know that the total torque is going to be equal to what? What's the total answer when I sum all the torques together? What is it going to be? Not 180. In the last problem, we added all the torques and we got 22.5, right? Or no, 57.5? That was the sum of the torques. So that meant because it was 57.5, it was rotating.
It should be 0.
Why 0?
Because it would.
Yeah, we want to know what should R be to produce rotational equilibrium. Forget the second part of the question. First part is what should R be to produce rotational equilibrium. Rotational equilibrium means that when you add all the torques together, you get what as an answer? 0. So if I look at this and I look at torque 1, torque 2, and torque 3 all separately, all I know is that when I add them together, they better add up to be 0. So let's start with the 15 Newton force. How far away is this 15 Newton force from the fulcrum? How far is it between these two locations, people? 10 meters, right? Is that clear? Please don't answer 4. The answer is 10 here, right? R is 10. Between the fulcrum and the 15 Newton force, this distance is 10 meters. The force applied is 15 newtons, and the angle is 60 degrees. Remembering here that this would cause the object to rotate clockwise. We call clockwise negative. If you need to write this down again, write it down. This is negative. This is positive. There's your nomenclature at the top. Okay, those are your rotations. So the rotation clockwise is negative. The rotation counter or anti-clockwise is positive. So this first one is going to be a negative symbol here. Again, why is this a negative symbol? Because this would cause it to rotate like that. Let's do the second one as the 10 Newton force that also causes the same rotation. So I know that that's going to be a negative torque. It's at a distance r, we don't know. Its force is 10 newtons, and it's the sine of 45. Again, why are both of these torques negative? Because both of these torques together would cause clockwise rotations. Each of these would cause clockwise rotations. But the last one, our saving grace here, without this, would this even be feasible, this problem? No, because you couldn't have rotational equilibrium if you don't have a balance. So that without this force, these two together could never produce equilibrium. Because these two together would cause it to just rotate all day like that. But this one is preventing the rotation by pushing back this way. So this is our positive torque, and that's at a distance of 6 meters from the fulcrum, a force of 25 newtons, and my angle is 90 degrees. So those are my 3 torques acting on this body. The idea is that if I add them together, what should I get as an answer? 0. So go ahead and write an equation at the bottom that adds those three together and set it equal to 0. You could even get a number for each of these if you'd like to, but you should be able to do this. Okay, the third one is going to be 6 times 25. That's just 150. I know that. The second one's negative. The first one's negative. But I don't know those numbers because I have to do sine of 45 and sine of 60.
First one's 129.9.
Negative 129.9. The second one's going to be, let me guess, 7.07,
So it's
Right.
just
R. Notice there's an R in here, guys, right? Where does that R come from? What are we trying to figure out? We're trying to figure out that R value right there. And 10 times 0.7071 is 7.07. And that is going to equal 0. So this simply becomes solve for R, right? Determine the value of R. Well, this is negative. This is positive. Combine those like terms first. Move the 7.07R since it's negative. I move that over to the other side. And then divide by 7.07.
Oh, we're just gonna ask how we know. Cause like I got stuck because it was only like an R, and I thought I had to simplify R before I do the total.
No, because you have like terms, right? These are like terms right here. So start by combining like terms. When I combine negative 129.9 to 150, I'm going to get 20.1. And I have negative 7.07R. So I'll move the 7.07 over by adding it. And then divide by 7.07.
That's 2.84.
2.84 meters. Okay, again, what did we do? We added together those three torques at the top. The three torques you see at the top, we added those together. And we said, if this is rotational equilibrium, which you probably want to jot this down, right? Rotational equilibrium means that the sum of the torques equals 0. Okay? Here's how you can write it easier. Ready? Sum of the torques equals 0. This is what's called rotational equilibrium right there. It's the same thing as with forces, right? If something was in equilibrium, the sum of the forces acting on it equals 0. If I'm having an arm wrestle with somebody, right? And I make it even better. If I'm just pushing against somebody and this is balanced, the forces are equal, right? So an arm wrestle, when you're locked in an arm wrestle, it's actually a balance of torques. Think about an arm wrestle. The longer arm, is that person usually better in an arm wrestle? You have more leverage. You have more of a lever arm. It's not a coincidence they use these words. Think about an arm wrestle. If my arm was only this long, like here, I would have very little leverage, or I could barely move. But if I have a longer arm, I can push down a lot more. I get more torque on it by acting with a force at a further distance. So the longer your arm is, the better you are in arm wrestle for that reason. Okay? Hey, we're going to finish this up tomorrow. We'll do some more stuff in class. If you want to start the homework, though, for grade 3, you can take a look, okay? So we have 2 more problems I want to go through. You can start multiple labs. You all get credit for labs, yeah, but you don't have to turn them in. Just put them in your books so you have them, please. So we talked about this question yesterday. We talked about how these forces produce either positive or negative torque. For those that weren't here yesterday, because a couple were out, can somebody explain quickly what torque is? What's torque? How would you describe it from yesterday? Yeah, it's a force applied that causes something to rotate. Or maybe it doesn't cause it to rotate because there's a reaction torque. So for example, I can give you a quick, simple analysis. If I were to open this door, I would open the door here because the pivot point is right here. This is my what's called lever arm. Remember that yesterday? Lever arm. If I push the door here, it's working. If I push it right here, it's almost impossible, right? When you open this door, because I have no leverage. You use the word leverage. If you ever used a crowbar or a hammer, the back end of a hammer to remove a nail, what are you doing? You're using a lever, really. The head of the hammer is your pivot point. The head of the hammer is your pivot point, and the actual back of the hammer is your lever. So if we look, and you see, if you ever want to remove a nail, You take the back end of a hammer. You take the. That's been there all year. You take. It's been there since last year, since the beginning of last year. No, just that one cabinet is a tool cabinet. Yeah. The others have tools, but they're not hung up nicely.
It's like stupid. It's like stupid. You just see stupid way like push that button.
So you take the hammer, right? You take the back end of a hammer, put it underneath the nail, and then what do? You pull back like this. And think about it. Here's your lever arm. This is the length of the lever arm. Here's the force, my hand. Here's the pivot point, the head of the hammer. When I pull back, I'm literally just pivoting, causing the nail to get pulled out of the surface. So it's a force applied over a certain distance. No, I shouldn't say distance. A force applied a distance away from the fulcrum. So if I wanted to lift this off the ground and I wasn't able to physically lift it, I could take a board and stuff that board underneath it, walk to the end of the board, and stand on the board. Because I'd be really far from the actual rotation point, and as a result, I would get a lot of leverage and lift it up. Okay, usually you put like a little object in the middle, so it acts as like, remember we talked about a seesaw yesterday? Okay, it's the same concept as a seesaw. You put like a little rotational thing right here, a little cylinder, put the wooden plank there, get on the other end, step on the other end, and it'll lift up that other piece. Okay, whatever is funny. You guys are all laughing right now. So whatever is funny, it's just, so think about the word leverage. The word leverage actually makes sense there. Let me think. What else? What else did we talk about yesterday? Oh, it's also a function of the angle. So let's take a look at this. The 25 Newton force, because it's at a 90-degree angle, does more, or has more torque in a sense, than the 15 Newton force, assuming they were at the same location. This one is further out, so this is going to provide more torque because of the length of the distance from the pivot point, but this one is at 90 degrees. And if you've ever used a wrench or a hammer or anything, if you have a wrench, you apply the force perpendicular to the wrench. Here's the bolt right here, here's the body of the wrench, and you literally push, and you push perpendicular because you get more leverage. So the goal, or the best angle, is 90 degrees. If I were to push this object from the left like this, what happens to it? If I push this way, what happens if I push directly in parallel to the lever arm? It wouldn't move. Nothing would happen. Because where's the rotation point? Right here. How do you rotate about something? You have to actually have a force that's at an angle to that object. But if you push directly this way, it would be like me. I gotta give an example. It'd be like what did I do yesterday? The ruler. Yeah, it wasn't a great example. Right? I feel like I screwed that one up. I don't know. I mean, I think you got it, but I feel like I screwed it up. Think about like a door, one of these little doors here. Yeah, it's a perfect example. If I want this door to rotate, I'm pushing this way, right? Now if I do this, is anything happening? No, because I'm literally pushing into the axis of rotation. I need to push it about or around the axis of rotation. So if theta is 0, you get no torque. If theta is 90, you get the most torque. Anything in between varies directly. We talked about that yesterday, okay? So 0 is no torque, more torque, more torque, more torque, the most torque possible at 90 degrees.
If a problem doesn't say what angle is, it just assume there's 90.
Yeah. If a problem ever doesn't give you an angle, the assumption is that it's automatically 90. It would have to be given in a diagram or specified. Here we have a diagram, so we know these angles are given. There's no problem. Now, we calculated the torque as a result of all three of those. Torque because of 1, because of 2, because of 3. When were things negative? When were things negative yesterday? Think back. When was a torque negative, Juliet? Yeah, we called it this way, and again, it's like calling down negative and up positive. Does it really matter? No. If you call up negative and down positive, life still works. You just got to remember everything down is now positive. So we're considering counterclockwise like this to be positive. So clockwise would be considered negative, and that's what we drew at the top here to remind ourselves. I always draw that when I'm thinking about a problem like this to remind myself if it's negative or positive. That's where these signs are coming from right here. Okay, bless you. That's where these signs are coming from right here. They're not coming from like a negative force or a negative distance, anything like that. You just apply the sign based on which way it would rotate. The last part of this problem, we calculated the actual distance that force should be applied at. It's delayed, there we go. And we got 2.84 to be that distance. And if you go back to the diagram, we'll see in the diagram that we're looking at that R value right there. So we did the first part of this problem. It said, where should it be in order to produce rotational equilibrium? The second part says, is the rod also in a state of force equilibrium? So this is just kind of like one of those questions that I asked to revisit old stuff. How do I find if something is in a state of force equilibrium?
If they equal each other.
Yeah. So if these two forces are pushing and equal, you're in equilibrium. But if this arm is stronger than this one, now you're not in equilibrium. So we need to look at our scenario. We have forces pushing down in this one. 25 Newton is down. 15 Newton is up and to the right. Look at the diagram, right? Up and to the right. So this is positive x, positive y, positive x for 15. The 25 Newton is only down, so negative y. How about the 10 Newton? That's down and left. So it's going to be negative y and negative x. You follow what I'm saying? Think about the way it's actually pointed. If I
positive y, you think of it like
for this,
well on that side, like if you think about
this is positive y and positive x. This is negative y. Remember, we're not looking at rotation now. The question was, is it in a state of force equilibrium only? And then here it was down and to the left, so negative y, negative x. So if you want to figure out if something's in a state of force equilibrium, we need to actually look at the x and y direction for these. So let me try and squeeze this in red here. I'll do the x first in red. Everything's delayed, guys. I'm sorry. AirPlay's not. Hold on. Let me reconnect to AirPlay. Give me a sec. The 25 Newton force only acts down. So as a result, we don't have to worry about an x component of that. How do I find x components of anything again? What's the rule? Take f times what for the x component? Cosine theta. Okay, remember it's f cosine theta for x, and for y it's f sine theta. So for the 10 Newton force on the far right over here, it's going to be 10 cos 45. Since it's acting to the left, I'd put a negative for the x direction. Again, this is kind of a review. This last question, is it in force equilibrium? This is a review of just Newton's laws and forces. So because this one is pushing down and left, I'm looking at the left component in the x. What would the y component of that force be? If it's 10 cos 45 for the x, what's the y component of that same force? What is it going to be?
Negative 10 sine 45.
Yeah. And why is it negative? Because it's pushing which way? Remember, we're not looking at rotation now. Down. Okay? The first part, we already did the rotation. So this force is pushing left and down. That's negative in the x because it's left, and negative in the y because it's down. So those are my components in the x and y for the first force. The 25 Newton force only acts down, and that only acts in the y. So I'm going to put minus 25 right here. Only in the y. This is just like we did, remember, vectors, where a person walks through the park. They walk 5 miles north, 2 miles at a certain angle northeast and south. You have to break it up into x and y and add all your x's and add all your y's. It's the same thing again here, what we're doing. How about this? Yeah. Because it's acting down. In the y direction, down is negative and up is? Remember, guys, this, what I'm doing now in red and blue, is not rotational at all. Forget clockwise and counterclockwise for this part. I'm simply looking at the forces alone. Imagine if I were to recreate this diagram and I literally did this. I put a point in space and I went like this. Well, there's a 10 Newton force. There's a 25 Newton force. And there's the 15 Newton force. Okay, this is how I'm analyzing this problem, as if it's a point in space and not a rod. Okay, that's really the scenario. I'm drawing a free body diagram of that on the right because that's where the sum of the forces is coming into play in x and y. Remember we did sum of the forces equals ma? That's what I'm really doing right now. Sum of the forces in the x is in red. Sum of the forces in the y is in blue. Bless you. But we still have to take into account this last force over here. This is pushing up and to the right. So it's positive in the y, positive in the x. So already I can know that my signs are going to be positive in the y and positive in the x. To find the x component, I take the force itself, 15, times the cos of 60. And to get the y component, 15 sine 60. Now, I'm not going to write equals ma here. I'm just going to leave it like that and add up the numbers. If it's in equilibrium, what should the numbers equal? 0. Guys, remember, equilibrium, 0 is your favorite number for that, right? If it's in rotational equilibrium, there's zero torque in the end. If it's in force equilibrium, there's zero forces in the x and y. So simply put, try to add these numbers together. If you get zero, it's in equilibrium. If you don't get zero, it's not. That's really it. Now, we know that if you don't get zero, you can know what the net force is, use F equals ma to find the acceleration, but this is a rod, it's fixed, it's not moving, so there's not going to be acceleration. There'll just be stress on the rod. Okay, it'll just be like stress. Imagine like a diving board. When you stand on the end of a diving board, you're stressing the material, right? You're causing the diving board to bend a little bit, so you're putting stress on it. So in this case, if there is a net force, it's not going to cause acceleration because this is fixed. It's drilled into the wall. If you remember from the lab yesterday, I used those, where they're in the cabinet. I used those little things and I put it up here and I said, here, this is your pivot point. So it's like you took a drill and you drill the rod into the wall. If you apply all these forces, it's going to cause it to turn and stuff, but it's not going to move left or right or up or down because it's drilled into the wall. So you're not going to have F equals ma here. You're just going to look at the total force. And if the total force is zero, you're in equilibrium. If it's not, you're not in equilibrium. That's all you have to do here. You don't have to go into any more detail. What do you got?
Oh,
Okay. Well, ask a question.
for the math, when you get the sine or cosine, what you're gonna go to the 10th, the hundredths.
Well, what I do is I put it all in one line
Oh,
instead,
okay.
so you don't have to round.
Yeah. Okay.
But for sine and cosine, keep 2 or 3 decimals until the very end, and then round.
Okay.
Okay, but just to be safe, just put this entire line in one entry. Put this all in one entry also.
So we would use this if you ask, oh, is this object?
Correct. And specifically though, force equilibrium. See that? In a state of force equilibrium?
Yeah.
Because earlier, what did we do? We wanted to find out the value of R that produced rotational equilibrium. And that's why we found the torques and set the sum of the torques. Remember we did this yesterday? Here it is. We set the sum equal to 0. That's what we're doing now. We're saying, do the forces add up to 0? If they do, it's in a state of force equilibrium. If they don't, it's not, meaning that the member itself would be stressed. There would be some sort of, it would like flex a little bit, okay? It would bend. What do you get for x and y when you add these numbers? Are they 0 pretty much, is what I'm asking? Did you get 0 when you added them up? No? What do you got? I don't remember if they are or not, honestly.
So the cosine for
Uh-huh.
x, I got point. They are. Oh, for x, I got 0.428, 0.43.
Which is close, but it's not 0. Good. And the other one?
And then for y, I got negative 19.08.
All right, something, yeah. And it doesn't. At that point, we could say it's not in force equilibrium, right? Because it's not 0. So what does this mean? It means that really this object feels a force to the right, right? Positive in the x, to the right, and down, negative in the y. The overall force was negative in the y direction. See negative 19 here? Which means that it feels a force down, because the y direction is either up or down. When you see a negative next to the 19, it means down. And then the x direction is either left or right. Since 0.42 is positive, it means it's feeling it to the right. So this object is this right here. And all these forces are acting on it, and it's not moving now. It's not moving. It's in a state of rotational equilibrium. But it's not in force equilibrium. So what might happen? Remember how I said you drill through and fix it to the wall? If you apply enough force, this might snap the bolt or the screw itself. If the bolt can hold up to like 50 pounds of force, in our case we want newtons, but say 50 newtons, it wouldn't snap. But if this screw could withstand, say, only 10 newtons of force, and it's feeling 19 newtons of force overall, it's going to break and it's going to shear. When a bolt shears, here's what it looks like. You take the object and imagine, so this is a bolt, okay? You go through the wall, it gets fixed on the other end of the wall, bolt looks like a screw, and usually it's holding things together. Shearing is when you're pulling on it like this, but this is held constant. So hold this still, and if I pulled on this hard enough, it could snap right in the middle is where it would snap. And what happens to bolts is if enough stress is happening, it shears and literally it snaps in the middle. I actually talked about this last period in engineering. We were talking about disasters and engineering ethics, and there was a hotel, the Hyatt Regency, in I think it was like the 70s, where they changed the design of the structure, and instead of having a solid, continuous cylindrical rod that went up to support all the different floors, they put what's called a box beam halfway there, and they connected 2 of them instead with bolts. And the designs that the engineers created did not call for that, but because of material problems, they replaced a single continuous rod with 2 separate ones that were joined in a box beam. And what happened? It sheared. Exactly what we're talking about here. There was too much stress laterally, and it snapped the bolt. The third floor fell into the second floor crashed into the atrium or the lobby, and it killed like 150 people. So it was a big deal, and it was in the news for a while back, when it happened. But this is exactly what's happening here. This is what would be happening if the net force acting on the object overcame the stress allowable from that rod or that whatever it is, in this case, bolt or screw. Okay? Overall, though, what are we getting from this? That the sum of the torques was 0 because it was in rotational equilibrium. We found the overall torques for each of them right here. We took those values. We got numbers for these 3 values, plugged them in right here. The first one was this. The second one had an R in it. That's why there's R here. The third one has a number. And we set this equal to 0 because there was no overall torque. And we solved for R. Okay, that was really what I wanted you to get from this problem yesterday. The other stuff was kind of like a follow-up, right? Like those problems I do where I do a little bit more for those ones. But what you want to focus on is the rotational part for this part. Okay, the rotational. All right, let's take a quick look at this example. So a wooden square, imagine like those little wooden blocks you can rotate.
Like the homework, the last 2 questions were asking something different. I just wonder if we're going to go over that. It was asking about like how to find the weight of a child whose 2 parents were doing it up on like a wooden beam or something like that. We're going to do that in class.
Yeah, you could actually have done that. I'll explain. Give me a second. I'll go over it. Just at the end of the period, remind me, okay? So a wooden square has a length of 1 meter. So 1 meter is actually pretty long, right? Meter, not this long. So we're talking about a big wooden thing that's pegged to the wall. It's fixed to the center. So this might be at a machine shop. Okay, it's an easy way to think about this as an analogy. Now our force is acting on this thing. 1 in 8 newtons, 1 in 4 newtons. So is it in a state of equilibrium for forces? No. 8 is more than 4, so it's not in a state of force equilibrium. Now, the question about rotational equilibrium comes up next. It says the square is subject to these forces and rotates. Find the net torque acting on the object. The net torque. And net, again, what does net mean? We need to know this word. Total or overall. Total or overall. The 8 Newton force. Which way will this spin as a result of the 8? Cover up the other one. Remember, cover up the 4 Newton force. And think about only pushing like that. Which way would it rotate? Would it rotate counterclockwise or clockwise? Counterclockwise. Think about it. Ready? Get rid of the 4 newtons. And if I were to push this way, this thing would spin like that. Does that make sense? The 8 Newton force would cause it to spin like this. And that's counterclockwise. So the 8 Newton force causes a positive torque. The 4 Newton force causes a negative torque going this way.
But would you still spin counterclockwise with the 4 newtons?
It absolutely still, and that's what we're going to prove mathematically, yes. Because why? One is more than the other, right? The question is, what's the lever arm? What's the lever arm? Remember this? Lever arm had to do with the distance between the point of rotation and the applied force, but it's always the perpendicular distance. It's a little bit tricky. That's why I'm asking this question. Just think outside the box. What do you think?
If the axis at the half, then that'd be 0.5.
Yeah. Very good. Now, why is it 0.5? Why isn't it this value, whatever this would be? Because that's really, if I think about it, that's how far apart they are, aren't they? If I look at the force and I look at that red line I just drew, are they perpendicular to each other? Are they? It looks like this angle is bigger than 90, right? I should have heard a no from everybody. That's much bigger than 90. So they're not perpendicular. So the lever arm is not that distance. What Ernest said a moment ago is exactly what we're looking for. It's actually that distance right there. Because if I continue this force, propagate the force over, like continue moving it in that direction, now aren't they perpendicular? So the distance, or the lever arm in this case, is only 0.5 meters. Okay, again, I'm not really looking at the force, so I'm going to erase that so you're not confused. But it's that distance right there, that's 0.5 meters. That's the actual length of R in both cases. Okay, so here's what you do. If you have a solid object where the point of rotation is in the middle of it, and you have a force acting on the outside, you continue drawing that force across. It's a technique I learned in engineering school, how to do this. This is like one of the first things we learned in mechanics of solids with torque. You take that force and you continue applying that force until you meet a perpendicular location from the point of pivot, the point of rotation, the pivot point. So you continue pushing the force along and see when will it become perpendicular between that and the actual value where the rotation or location where the rotation is, and that's where it's going to be. So the same thing for the 4 Newton force. You continue over, as if it's acting right there, you write it, so it has the exact same distance from the rotation, which is 0.5.
Is it safe to assume the rotational spot is from the center?
Here it is because it says it, actually. Right? Here it says that it's free to rotate about its center axis.
Technically, we can't assume that.
No, you can't assume anything there. I could have done this, ready? What if the point of rotation was here? Right? Now, the distance of the lever arm is from here all the way up to there.
Except it wouldn't be as easy to find the distance.
No, you'd have to be given that value or given some other information, right? Like this would maybe be, if this was 0.2, then that's 0.8. You know what I mean? But you need to be given some other piece of information. So if we look at the torque from both objects, since we're finding the net torque, we know the formula is RF sine theta. What's my theta since I approached it this way? Theta is 90. Because if I look at the distance in the blue, let me erase the one I just drew actually. Hold on. So if I look at the distance in blue, that 0.5 meters right there, that distance, or that axis, that lever arm here, is perpendicular to the red. So the angle is 90 degrees in this case. A lot of the time when you're not given an angle, you want to look for when it meets perpendicularly and always use 90 degrees. If you're not given an angle and it's an object and it's like it's being pulled arbitrarily, you want to go ahead and try to figure out, well, what is the distance here that would make this 90 degrees? So it drops off this part of the problem. Okay, sine of 90 is 1. Sorry, sine of 90 is 1. So it doesn't affect the problem at all. So it becomes the lever arm times the force. Now, because this is causing it to rotate counterclockwise, the 8 Newton, right? We're talking about this as tau 1. That's causing tau 1. We call that positive. So the answer is simply 4 Newtons here. And then tau 2 is R times F times sine theta again. But again, sine of 90 is 1. So it doesn't affect the problem. So it's simply half of 4. But because it's going to cause it to rotate the other way, this one is negative, so that's negative 2, and these are Newton meters. So the 8 Newton force caused a torque of 4 Newton meters. The 4 Newton force caused a torque of negative 2 Newton meters. Again, positive is this way, negative is this way. So which one is bigger? Obviously the one that's provided from the 8 Newton force because it's more force. Same lever arm of 0.5, so more force means more torque. So the overall torque is the sum of all the torques. You don't have to write this out, obviously. It's pretty obvious, right? Which is just simply 2 Newton meters. So what does that mean? All it means is that the 8 Newton force was stronger than the 4 Newton. Since they both acted with the same lever arm, that stronger force created a stronger torque. The stronger torque created a positive torque, which means that this object will rotate counterclockwise. Okay, that's what George asked in the beginning. He was like, well, you know what? Even though this pushes it clockwise, this one pushing it counterclockwise is stronger with the same distance, so isn't it going to naturally just go this way? And yes, it is. A positive answer tells me that it's going to rotate counterclockwise. Okay, counterclockwise. Let's look at this last example. So if you've ever, I'm trying to think of an example of this. You ever seen like a conveyor belt where they have like, have you seen like any shows or like you look at like a manufacturing plant where they have like they're moving boxes along a conveyor belt, or a tank? A tank has a conveyor belt on it, the chain link around, or not the chain, but the actual, what is it called? Anyone know what the word for that is? The treads that lock onto the actual rotating mechanism. The angle that is produced is always tangent. It's always tangent. So we're going to talk about tangential motion soon in actually the next lesson. We're going to talk about it. So this is a good kind of preview to see this. If I were to pull on a rope and the rope was attached to a pulley, I'm always pulling tangent to the rope or tangent to the pulley itself. I have a bunch of pulleys up there. Maybe I'll put one together tomorrow to show you. So if you literally pull on something, so imagine this is like a rotating axis. This is a pulley system. Okay, it's two wheels that are connected, the inner and the outer wheel, and there are 4 ropes attached. And those ropes are connected to different parts that apply forces on them. Now, if I think about this, let's only look at one of these for a moment, okay? Let's isolate one. Let's look at this one right here. If I look at this force right here, I can see that this force is applied right here. That's the point of location where it's applied. Now, the distance from the rotating point, where's the rotating point? In the center in this case. The distance from there is what? Between the force applied and the center, what is that distance? Don't give me a number, give me like in variables in this case. Not just r. Be careful.
R squared.
Not r squared.
R1.
The inner wheel, the distance would be r, but I'm going from here all the way out to here.
Yeah, so
No.
Oh, wait, what's that right
Oh, 2R.
It's in the diagram over here.
Yeah.
Okay? Yeah, it's not next to that force though, okay? But the distance from the center to the inner wheel is r, radius r. The distance from the center to the outer wheel is double that, 2r. So this force that we're seeing here, let's point it out again. This force is applied at a distance 2r. This is a perpendicular distance. Look, I'll draw it so you can see. Okay, that's 2r. And that distance is perpendicular from the rotating axis. So again, an example where you're not even given angles. What are the angles? What are they all going to be? 90 degrees. Okay? Now, which way would this cause it to rotate? Counterclockwise. How about this one? This one? This one? Clockwise also. These three are all clockwise. Because it would all rotate to the right or this way. Right? It would rotate this way as a result of these three. So this is not a difficult problem, but you're not given any numbers, right? You're not given any numbers. So you're really doing this in terms of R and F. So we need to look at the torque from each of these. Okay.
What would rotate for R be? And through which direction?
What would the what be?
The
R are just dimensions. Those aren't forces. Sorry. R is radius, it stands for.
Oh,
That's a dimension. So this is an old diagram, but the way I like to draw dimensions is with a double arrow.
okay.
So if you want to think of it that way, does that make better sense?
Yeah.
And it's the gap here. There's only 4 forces. That's it.
Okay.
Because forces are drawn with arrows. Distances or like dimensions should have a double arrow on the end of it. So anyhow, we take a look at this one and we think to ourselves, okay, we've got 4 torques acting on this. And the question is, do these forces cause the wheel to rotate? What's your guess right off the bat?
Yes.
And can you prove to me that you're right just by looking? What could tell you that you know you're right? Ernest.
They're all moving in one direction, so it's not like an opposing rotation.
Well, no, there's one that opposes right here. This one goes counterclockwise. These all go clockwise. So it's 3 versus 1, really.
Yeah, I think that's right. There's more forces acting in that direction.
All right, but that's not necessarily. The forces could be 2 and 3 and 4, and the other one could be 30.
But since that's 2F, wouldn't that technically mean that no matter how high that is, it's double that?
Yeah, this torque is double that torque, right, in force.
No matter what.
But the lever arm is half, so you can't assume that. There's one reason you can see that you know it's going to rotate clockwise. One of these forces cancels with this one. Think about it, right? How far away from the center is this force? How far away is that? 2r. How far is this force? 2r. How is this one? 2r. Well, this 2r is causing counterclockwise. This force at 2r causes clockwise. So really, you could think about the fact that these could really just cancel each other out. And then you're left with only these 2 here. I'm going to show that mathematically that they do cancel. But we'll find the torque from all 4 of these. George?
So then could you say 3F in now?
You could think of 3F, but there are different distances from the rotation, aren't they? So the R value here is R. What's this value? 2R. So we're not going to use 3F, but F will be used for sure, but you can't sum them together. It's a good question, though. It has to do with the actual distance from the rotating axis that we have to consider. So let's look at the first force that's going. Let's look at this one here first. I'll point to it. This is the only one that's causing a rotation counterclockwise, this force. So that's going to be our only positive torque. So we've got a force at a distance of 2r. Again, that's this one right here. So let's check it off so we've done it. And that's the one we did. Again, the force applied is F. We don't have a number. It's some value. The distance from the center is double the radius of the inner one, 2r. Well, then we go to the next force right away and look at this one right here. Look at the other one I checked off. This one is going to cause it to rotate clockwise. What kind of a torque is clockwise considered? Negative. So the next thing becomes negative, and then what's the torque? Well, it's just F, which is the force right here. And how far is it from the center? 2R, again. So what happens to those right away? They cancel. Those values are going to drop off from each other. So really all we have to look at is these two torques, or these two forces at the bottom. So let's look at our next one. This is another minus F times 2R. Because again, this force is F. The distance from the center to where the force is applied is 2R. It's going to cause it to rotate clockwise, so it's negative. And then finally, this last part right here is a force of 2F, but the distance is only R now. Look at the distance from center to here. It's only R, but this is double the force. It's still minus, but it's now 2F times R. These are the same thing, aren't they? Double FR, double FR, double FR, double FR. They're all 2FRs. The first two cancel each other out. Right? I've got 2 FRs minus 6 FRs, if I think about it that way, yielding negative 4 FR. Or I could have done it by saying, you know what? Cancel, cancel, add these together. This becomes negative 2 plus negative 2, or negative 4 FR. Either way works to look at it, right? But what's the idea? If I get a negative torque as an answer, what does that allow you to conclude based on what was the question? Do they actually rotate? Yeah, they do. When would they not rotate? What would the answer be? Zero. Whenever the sum of all the torques acting on something is 0, it means that it's in a state of rotational equilibrium. If it's not in your head right now, you should probably write that down. Right? If the answer were 0, this object wouldn't rotate. Therefore, dot, 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 right? The 3 dots, the triangle dots. Therefore, it's in a state of rotational equilibrium when you get 0 net torque. In this case, no. We don't get 0 net torque. We get some value. If the force was 20 newtons, that goes here. If the radius was 7 meters, that goes here, or whatever it is, right? That gets plugged in. But you're solving this problem in terms of all variables. They're simple variables, though, in this case. They're not really complicated. It's not like you're using x and vi and vf and t, right? It's literally F and R. That's all you're looking at here. Force and a lever arm. Okay? About 7 minutes. I wanted to start the next lesson, but it's not worth starting it right now. It's fine, though, because we're good on time, so we don't have to rush. Homework I gave you is here. Let's actually address that question. So, Ernest had a question. What number?
It was 56 and 58.
All right. So let's take a look at those problems real quick. Maybe it could give us a little insight to help us tonight. So remember, this homework's due tomorrow. Okay? Please make sure to get it done before then. On page 296. All right, on page 296, number 56 and 58. So 56 says, if two parents did you look at the figure, by the way?
Yeah.
Okay. In figure 8.19, exert upward forces of 18 newtons on the left and 71 on the right, how much does the child weigh? So let's go through this. So it says, see the figure. So this is on page 296, but the figure is 8.19, which is on page... You saw it already? This is number 56. There it is.
Yeah.
Okay. So this is number 56 on page 296, but the figure that they're referring to is on page 290. Here's what the figure looks like. There's an axis of rotation here. I'm drawing, here, take a look quickly. Take a look up, look up, look up. This is the figure. This person here is the mom, here's the dad, here's the kid. The axis of rotation is a bolt at the end, so I'm literally drawing that. But I'm not going to draw people. I'm just going to draw arrows for forces. So the mom lifts up at the end with a force F1. At the point of rotation, she pulls. The dad pulls up with a force of F2. The kid weighs mg, and it says that the entire length is L, and the kid is 3/4 of the length L, and then this is 1/4 of L. Okay, that's what's happening in this problem. This is the weight of the kid sitting down. He's sitting on a beam. The mom's holding this end. The dad is holding this end. And it looks like the dad is about to like flip his end and cause the kid to rotate for some reason. I don't know what they're doing in this problem. 2 parents support a kid on a plank. I don't know why they're putting a kid on a piece of wood and carrying him. It's very unsafe, but in case you want to do that one day, put a kid on a 2x6 and see if he survives. So here's the scenario. And the question says this. Here's what the question says. If the mom exerts a force of 18 newtons, so that's F1, and the dad exerts a force of 71 newtons, F2, how much does the child weigh? Now, there's a huge assumption that they don't put in this problem. I don't love the problems in this text. The text is good, but the problems aren't always great. The assumption is that it's in rotational equilibrium. You have to assume that, or else you can't solve. Yeah. So think about this. You've got this object, or this force applied at a distance from the fulcrum. So this applies a torque. This object at a force at a distance from the fulcrum. This applies a force. Does this do anything? What's the distance between this force and the actual rotating axis? What's the distance?
0.
So when you do RF sine theta for the torque from this, yeah, F is 18, but what's R? R is 0. So it's the same example as what I did a minute ago, right? I push on the rotating axis. Am I applying any torque? No, I can't. It's closing. So when you push where it's rotating, R is 0. It makes no sense to push on a hinge and assume it's going to rotate. So the mom that's lifting up, assuming this, for some reason, this is the point of rotation, like it's fixed. It's not a good example with the figure. I would think of this example as more, you drill something to the wall, and on one end, you've got a support pushing up, like maybe a rope pulling upward. On the other part, you've got a kid sitting in the middle, maybe like that. And the idea is that you want to set it equal to 0 for rotational equilibrium. So you've got 71 newtons, right, is the force, times the distance. What's this distance? The overall length. What would you call that? It's a variable. What would I call it? L, right? 3/4 L plus 1/4 L is how many quarters L? 4 quarters or a whole. Okay. If you don't know your fractions well, think of quarters, literally quarters themselves. If I have 3/4 in my hand and 1/4 in the other hand, it's $1, right? So this full length is L. So this is 71 times the length of L. This is mg, which is the force down, times the length of 3/4 L. Okay, and those are going to be negative and positive accordingly. So if I were doing this, I would think, all right, this one is going to cause it to rotate this way. That's going to be considered positive. This one's going to cause it to rotate this way. That's considered a negative torque. So when I'm doing the math behind this problem, I think to myself, all right, well, I've got torque 1 plus torque 2. That's what we're looking for. Again, the mom applies no torque because she's pushing on the actual rotating axis. I could use this, but again, R equals 0 for this force. The first torque, let's say we'll call that from the kid. We'll use that for the kid as the first torque. The kid provides a negative torque here, and the force applied is the weight, which is mg, times the distance from the rotating axis, which is 3/4 L. The dad applies a force of 71 newtons at a distance L. And if this thing isn't going to rotate, it has to be equal to 0. And again, the kid causing a rotation that is clockwise is negative. The dad, tau 2, causes a positive torque. And if I'm going to assume, that's the big assumption here. This problem doesn't even say that, which is annoying. It says if they exert this, blah, blah, how much does the child weigh? In reality, you actually have to figure out what the actual net torque is on this problem. So we go ahead and look at this and we say to ourselves, you know what? Let's just go ahead and solve. It looks like you can't. But if you're looking for the weight of the weight of the child is mg. So that's what we're trying to solve for. So I think about this as negative mg 3/4. Why can I get rid of my L? Yeah, divide everything by L. 0 divided by L, 0. And the L's in the other spots, just divide this. Divide by L, divide by L, divide by L. You can remember mass canceled out if mass was in every turn? Well, L is in every turn. It cancels out. So I'm left with this part. And as a result, I can just solve for the quantity mg. We're not trying to find the mass of the kid. It says, how much does he weigh? So let's go ahead and move 71 over. And multiply by negative 4/3 on both sides. Remember, you multiply by the reciprocal of a fraction always. Leaving on the left side simply mg And on the right side, whatever 4/3 of 71 becomes. 71, does that have a third and even third? No. It's going to be what? 25 would be for 75. What do you get? 71 times 4/3. Ernest, what do you got? Oh, I think I had it already, sorry. Yeah. 94.6?
Yeah.
It's got to go up because 4/3 is more than 1, right? So this is the weight of the child. That's what the mg value would be for this child. Now, again, if they said what's the mass of the child, how do you solve for m? If you wanted the mass only, what would you do?
You just said G and
Yeah, divide by 9.81. This is the weight of the child. The weight, what is weight? Weight is Fg. The weight of an object is the force of gravity. Fg is equal to mg. So we're really getting the whole quantity mg. Instead of writing mg in all these spots, you could have just written w for weight, even though we're not using w, or Fg for the force of gravity, and solve for that.
Isn't it unusual to write weight as a movie?
It is unusual to write weight because of the fact that w is used for work and watts. So instead of writing weight, usually you write Fg, the force due to gravity. Yeah. And then 58, I want you to think about. Oh yeah, I don't even have to tell you anything for 58. 58 is the seesaw. Remember the lab we did yesterday? Think about that for 58.
I didn't even see. I just saw 56.
Oh, okay. Yeah, 58 you can do for sure. Yeah, 56 was confusing because the diagram is not actually given in this problem. Okay, 58 you can definitely do. What are the others in here? 36,
Oh, this is just like
44.
we did yesterday.
Yeah, I think it's just calculating normal torque.
Yeah, it's just calculating.
Okay.